So in this section, we're going to talk about similar triangles. All right, so this is the way we write triangles. So two triangles are, what is that? Two triangles are similar if they have the same shape, but not necessarily the same size. So here's an example. These two right triangles have the same shape and the same size. But here's what I could do. Now, really, I've never done this before, so I don't know how this is going to work. But suppose I select this one over here, and then I drag it like this. You ever done this before, where you make one picture proportionally bigger than the other? So it seems to have worked. So now, if I do it like this, they're the same shape and the same size, and now maybe if I pull it down here, maybe it's the same shape, but everything's double, right? The lengths of the sides are double, and then maybe even down here like they're triple. But what happens as I do this is that the lengths of the sides are proportional, like maybe they're double now, but the measures of the angles are still the same. They haven't changed. So this angle here is the same as it was here. This angle here is still a right angle. These are still right angles. And this angle down here has remained the same. Those measures stay the same. So the measures of the angles stay the same, but the lengths of the sides are proportional. Like this side here might be double this side. Then this side would be double that one. This would be double that one. Or maybe this one is now 1.6 times as big as this one. This would be 1.6 times as big as that one. And this would be 1.6 times as big as that one. So these two triangles are similar. Now, if we do this, if we change the orientation, like if we take this one here and change its orientation, they're still similar, right? Because they still have the same angle measures and the sides are still proportional. So orientation doesn't matter. In the first problem we're going to do in this section, we've got these two similar triangles, and what we're trying to do is find the measures of the unknown angles. So it looks like we need the measure here, M, B, and A. Well, let's see, I think we can get B, right? Because B, these double lines are similar to those here. So this angle measure is going to be the same as that angle measure. So we can say then that the measure of angle B is also going to be that 103 degrees. Now let's get angle M here. So here's what we know, right? These three measures add up to 180. So we do know this. We do know that 13 degrees plus 103 degrees plus that measure of angle M, that's going to be 180 degrees. All right, so this is going to give us 116 plus angle M is 180, and then if we subtract that 116, we're going to get that angle M is equal to 180 minus 116 is 64 degrees. So far we've got angle B, we've got angle M. So what we need now is angle A. But if B is 103 and M, we just found M to be 64. I'll put a 64 up here, right? Up at the top I put a 64. So because the triangles are similar, we know that this angle here, angle A, has to be 64 also. So angle A has to be 64 degrees also. So in problem number 2, what we're going to do is we're going to assume that this triangle here, ABC, is similar, that's the notation for similar, to this triangle, A prime, B prime, C prime. Let's draw it. So maybe here is A, B, C, and then let's just make this one bigger, although we don't really know. But I'll try to make it bigger proportionally. And now, when we say similar, what we mean by this notation is that this A will correspond to this A prime down here, and B, this B will correspond to the B prime up here, and the C will correspond to this C prime over here. And now in my problem here, AB, this distance right here, the length of that side is given as 1.0 units. BC, that's given as 2.0 units, and AC, AC, this side here, is given as 4.0 units. Now, we're also given something here. We're given that the shortest side of this triangle, the shortest side, is 6.0 units. So just to make the picture correspond, the shortest side is 6.0. And we're going to try to find the other two sides. So we want to find this side and this side. So the way I've drawn it is this is the shortest side here. That's going to compare to the shortest side here, proportional. And look what we've got here. This shortest side corresponds to this shortest side, and this shortest side is 6 times as big as this one, right? This is easy to see without any crazy decimals. So what we've done is, like in this small triangle, we've enlarged it by stretching it out 6 times. So this side here is 6 times this side. That means every side here is going to be 6 times the corresponding side. So we know that B prime C prime is going to be, now that's this side here, that's going to correspond to this one, BC. It's going to be, all right, how we're getting it, it's going to be 6 times that 2.0. So B prime C prime is 12.0. And then A prime C prime, all right, that's going to be 6 times, well, this is going to be 6 times the corresponding side, which is 4.0. So we're going to get here that A prime C prime is 24.0. So there's the missing sides. Now in problem number 3 here, these two triangles are similar. Do you see it? This is 90 degrees, this is 90 degrees. This side is the same as that side, identical. That's because of the marks, they mean they're the same side. This side has equal length to this side. So because they're right triangles, this side here has to equal that side there. So these two triangles are similar, but they're even more than that. These two triangles are congruent. And congruent means that not only are they similar, but they have equal measures all the way around, meaning each corresponding angle is equal and each corresponding side has equal measure. That's what congruent means. So what they're asking us in this problem is, are they similar? And they're similar, yes. And not only that, but they are congruent. Well, let's see, I'm going to say that, of course, angle G, that corresponds, let's do it this way, corresponds to angle J. That's clear because they're both right angles. But I'm going to say, too, that angle E up here at the top, that's going to correspond to angle K up there at the top, correspond to angle K. And then this angle F at the bottom is going to correspond to that angle I. So angle F corresponds to angle I. And how about side EG? I'll put a line over it for a segment. That's going to correspond to, all right, that's this side right here, EG. That'll correspond over here to KJ. So that'll correspond to KJ. Maybe this bottom here will correspond to the bottom over here. So how about GF? That will correspond to GF with that bottom, IJ. And then finally, I think the hypotenuse here will correspond with that hypotenuse over here. So how about if we say EF corresponds with IK? Now in problem 5, we're given that this triangle here, ABC, is similar to this triangle here, PQR. And what we're trying to do here is find, okay, let's write down what we want to find. We want to find QR, so QR is right here. We want to find that hypotenuse. And then also we want to find PR. So find QR and PR. And PR is that base right there. So what we're going to do is set up a proportion. Here's what we know. That maybe this small left side is to the big left side. Small left is to big left. Let's write that. So small left is to big left. 10 is to 33 as, say, the small bottom is to the big bottom. So we could say that as 40 is to PR. Now this is a proportion, and we solve proportions by cross multiplying. I've got one fraction equaling another. We can cross multiply, and that will take us to here. We'll get 10 PR, how about if we do that, equals 33 times 40. So what I did is I cross multiplied. I got this one here equaling that product there. So this will give us 10 PR equals, now 33 times 40 turns out to be 1320. Let's divide by 10. So we'll get PR equals, okay, 1320 divided by 10. So PR is going to be 132. Now we've got these two similar triangles. We have this small one, ABC, right? This small one is down here similar to the big one, ADE. And we want to find the length of this side here, CA. Now that's a hypotenuse. So let's use proportions again. Here's what I see here. You see this, I have the big left side to the small left side. So let's write that as a proportion. We have the big left side is to the small left side as, and then how about the big hypotenuse is to the small hypotenuse. So the big hypotenuse, which is 9, is to the small hypotenuse, which is CA. And now we'll solve this by cross multiplying. So we'll multiply this way, getting 6CA equals now this way, 2 times 9. This will give us 6CA equals 18. Divide by 6, and we'll get CA, which is what we're looking for, is equal to 18 divided by 6. We get 3. Now in this picture here, we've got that this, on the left, this vertical line here is parallel to this segment over here, right? So this segment is parallel to this segment, and then we're given these values, and we want to find the length of EC. Now, we do know this, that because these two lines here are, these two segments are parallel, these two sides are parallel, that these alternate interior angles are the same measure. This one up here, A and B, those are the same measure. And for the same reason, D and C are the same measure. And because they're vertical angles, how about if we do it this way? These two angles have the same measure. Well, now because we have 3 corresponding angles like this triangle, this small triangle, is similar to the big triangle. So we know, and we can write that triangle AED is similar to triangle BEC. And that tells us that the sides are in proportion. So we could write something like this. We could write that maybe 7 is to 6 as 21 is to EC. Let's do that. So let's write 7, let's try to write it. Come on now. 7 is to 6 as 21 is to EC, and then we'll cross multiply. So we'll get this multiplication here, this multiplication here. So that'll give us 7EC is equal to 6 times 21. So 7EC is equal to 126. Let's divide by 7. And I get EC is equal to 18. So what we have here is a tree, a fine-looking tree, and a pole. And the pole is 7 feet high, and it casts a 3-foot shadow. The tree, we know, casts a 38-foot shadow, and what we want to know is how high is the tree. So why don't we let it equal x? That height will be x. That will be this distance from here to the ground. And we can set up a proportion. Now, there's actually several that we could write. How about if we try this one here? What if we go that the height of the tree is to the length of its shadow? That would give us x is to 38 as, then the height of the pole is to length of its shadow. 7 is to 3. And cross multiplication here is going to give us 3x equals 7 times 38. So that's going to give us 3x equals, that's 266. And now we're going to divide by 3, and when I do that, I got 88.66 is ... So how about this? Let's round off to 88.7 feet. So how high is the tree? Let's say 88.7 feet. You know, what we could have done here is set up a different proportion. The one we set up was, say, tall left side to short left side. We could have set this up maybe as tall left side to long bottom. So we could have set it up like this. Maybe we could have set it up as, say, x is to 38. The height of the tree is to the height of the tree is to the length of its shadow, as the height of the pole is to the length of its shadow. 7 is to 3. And then when you cross multiply, what do you know? You get 3x equals 38 times 7, which is the same as we got up here.